Assalamualaikum warahmatullahi wabarakatuh. My name is Putri Azalia with student ID 2206059111. So I will continue for explaining my examination from my previous video. So I will explain again about the student version military application of Spring Mass. So the next is initial thinking. So the first initial thinking is problem understanding and context. The objective is determine the best shock absorber for the suspension system of the satellite transportable terminal to prevent satellite damage. The context is the STD trailer is loaded with a satellite, make it crucial to avoid oscillatory motions and ensure structural integrity during transport over various terrains. Next is we have to identify the key parameters and gather data. The first is mass of loaded trailer is 1,800 kilograms. And then the initial displacement of shocks before loading 3 centimeters, shock specifications, spring constants for different shocks, damping coefficient for the different shocks. And the third one is formulate the differential equations. So this is the formula. M is mass of the loaded trailer, beta is damping constant varies for each shock, K is spring constant, X is displacement of the system over time, F is external force acting on the system. And the fourth is calculate the critically damped value. So this is the formula. And the action is calculate the beta critical for each shock and compare with their actual damping coefficients. So next is solve the differential equations. There is the initial conditions, homogeneous solution and non-homogeneous solutions. So we can see the formula. So use the analytical methods and software like Mathematica to solve these equations. So next is we must to plot the solutions. So the action is plot the displacement over time for shock, and the comparison is compare the result for given damping values and critically damped values. So number 7 is analyze shock performance. We can evaluate the maximum displacement, setting time, and oscillatory behavior. And we can check how quickly the system returns to equilibrium without excessive oscillations. So number 8 is determine the best shock for loading. The criteria is the cost, reliability, and effectiveness in minimizing oscillatory motions and protecting the satellite. And then we have to identify the shock that provides optimal performance according to this criteria. So the ninth is model the suspension system under the external force. So the external force consideration is like function t, it's equal to 100 sin for t. And the action is solve the non-homogeneous differential equation for each shock. And for the plot and analysis, determine the maximum and minimum displacement under this force. Number 10, we can evaluate the long-term performance. Consideration is long-term risks such as bottoming out and continuous protection of the satellite. Assess the shock's ability to maintain performance over time. Number 11 is address undamped shocks. Present data showing the inadequacy of undamped shocks in protecting the satellite. So argue against the use of undamped shocks based on the analysis. The 12 is conduct additional simulations. The scenario is rugged terrain and impulse forces modeled by direct delta functions. And for the tools is use computational simulations to analyze the system response to these scenarios. So the last one is document findings and the recommendations. Compile results and highlight the best shock absorber for these different scenarios. Recommendation is provide clear data-driven recommendation based on the analysis and simulations. So ensure all findings are well documented and supported by mathematical and simulations results. So I will clarify again the essence of this initial thinking, that our primary objective is to determine the best shock absorber for satellite transportable terminal suspension system to prevent satellite damage. We gather key parameters including the mass of the loaded trailer, it's 1,800 kilograms, initial shock displacement 3 centimeters, and shock absorber specifications. We formulate and solve the differential equation for the spring mass system, comparing critically damped values with actual damped coefficients. By plotting displacement over time, we analyze performance metrics such as maximum displacement, settling time, or oscillatory behavior to assess stability. We identify the best shock absorber based on cost, reliability, and effectiveness. Additionally, we model the system under the external force and evaluate the long-term performance to ensure continuous satellite protections. We present data on the inadequacy of enzyme shocks and conduct additional simulations and compile clear data driven recommendation for the optimal shock absorber, ensuring the STDs and satellites safety and functionality. So that's all my explanation about the initial thinking. Next, I will explaining about the idealization to solving this problem. Let's continue to the next video.